Let's open up a new file in Abacus. We'll rename the model Plate Bending Model. Let's create a new part. We'll name it Plate and we'll set it to type 3D deformable. We're going to set the base feature to shell. Now base feature shape literally refers to the shape of the part that we'll be creating. It doesn't refer to the type of analysis we'll be performing. In previous tutorials, we've selected point and wire, and you know that there's no such thing as a wire element or a point element. Similarly, when we select shell, we're only telling Abacus that our part is going to be in the shape of a shell. We're not telling it that we'll be meshing it with shell elements and doing a shell analysis on it. This is useful because when Abacus knows we're creating a shell-shaped part, it's going to give us the options that are useful to us when creating a shell, or maybe not give us options that wouldn't be useful when creating a shell. For example, if you selected solid, after you sketched it out, Abacus would prompt you to extrude it and give it some depth. Whereas if we go with shell, once we sketch it, Abacus knows that this is a shell, so it's not going to tell us to extrude it. As for the type, we're going to set that to planar because we're creating a plate, which, as you know, is a planar object. We'll set the approximate size to 20 and click on Continue. You find yourself in the sketcher. Let's use the Create Lines Rectangle tool. This will allow us to create a sketch of the plate. Abacus prompts you to pick a starting corner for the rectangle, and then to pick the opposite corner. Next, we'll use the Add Dimension tool to dimension our plate. Once we're done sketching the section for the planar shell, we can click the Done button. Create the steel material as you've done in the previous tutorials. Create a new section called Plate Section. Set the category to shell. Abacus offers you many different types of shells. You need to pick the correct one depending on the type of analysis you're performing. If, for example, your shell consisted of many layers of materials, you'd go with the composite type. On the other hand, if your shell was like a membrane, where it has strength in the plane of the surface, but no bending stiffness, then you'd go with the membrane type. In our case, we're going to go with homogeneous. The homogeneous type has stiffness in the plane of the surface and also has bending stiffness. Abacus will allow you to specify the thickness of a homogeneous type shell. Click on Continue. You see the Edit Section window. Abacus asks you whether to perform the section integration during the analysis or before it. You've seen this before if you think back to the beam frame example. If we know that the response of the shell is going to be linear elastic, and we're also not going to consider temperature or predefined field variables in this analysis, you can choose before analysis. On the other hand, if you're expecting nonlinear behavior, or you plan to account for heat transfer, you need to go with during analysis. If you choose that option, Abacus will calculate the section properties by numerically integrating through the thickness of the shell during the analysis. We're going to go with this option. Abacus needs to know what the thickness of the shell will be. We know that our shell will have a uniform thickness of 0.1 meters, so we'll specify a value of 0.1. If you had a shell with variable thickness, you could go with element distribution or nodal distribution, and that would allow you to specify a spatially varying thickness for your shell using a distribution. We make sure that the material is set to steel. Next, we need to set the thickness integration rule. A moment ago, we decided that we would go with during analysis for the section integration. In order to numerically integrate over the section, Abacus gives you two methods. They are Simpson and Gauss. The Simpson integration rule should be used if you would like results to be output on the shell surface. If you're using a composite shell, the Simpson integration rule will allow you to find the transverse shear stresses at the interface between two layers. Also, the Simpson rule must be used for heat transfer. On the other hand, Gauss quadrature should be used in cases where you don't care about the results on the shell surface. Gauss quadrature cannot be used for coupled temperature displacement or for heat transfer. By default, Simpson rule uses 5 section points for a homogeneous section, whereas Gauss quadrature uses 3 section points. You see the default value of 5 displayed for thickness integration points. We're going to leave that at this default. Next, we assign the section to the plate. In the Edit Section assignment window, Abacus asks you to specify a shell offset. Let me explain what this means. When you use shell elements, they're created as a surface called the reference surface, and this reference surface is where the nodes of the shell elements are. In reality, of course, shells have a certain thickness, so what you usually do is you specify the reference surface to correspond to the middle of the actual physical shell surface and specify a thickness. And this represents your shell in the analysis. However, sometimes when you import a model from CAD, you find that the CAD modeler has represented either the outer surface or the inner surface of the shell as part of the CAD model. And it would be incorrect to put the shell elements on this surface. So what you do is you tell Abacus to offset the reference surface from this surface. And you can do this by selecting one of the shell offset options. You can go with top surface, bottom surface, or middle surface. In fact, you also have the option to specify a value. This value would need to be a fraction of the shell's thickness from the shell's mid-surface to the reference surface. For example, if you set it to 0.5, the top surface of the shell would be the reference surface. If you set it to negative 0.5, the bottom surface of the shell would be this reference surface. In our case, we're going to select middle surface. Click on OK. Next, let's create the assembly. We'll import the plate as a dependent instance type. Then we'll create the step. Let's call it load step. We'll set the procedure type to static general. Let's turn on nonlinear geometry, or NLGEOM. This is because we can expect some nonlinear behavior in the simulation. Initially, the plate is only going to have bending stiffness, but once it's bent a little bit, we're going to experience membrane effects, or membrane stresses, which might increase the bending stiffness of the plate. We'll rename the field output, calling it output stresses and displacements, and we'll set it to output exactly what the name suggests. We're not going to request any history outputs for the simulation. In fact, we'll delete the pre-existing one. Right-click on houtput1 and choose Delete. While you're probably unlikely to do that in any of your actual simulations, I just want you to see that it's possible. Let's create the boundary condition. We'll call it fixEdge and apply it in the initial step. We'll set it to type displacement rotation in the mechanical category. Let's check off all the translations and all the rotations as well. This is going to fix the left edge of the plate. In previous tutorials, when we wanted to fix an edge, we used the Encaster boundary condition. Encaster does the exact same thing we just did. It basically constrains the rotations as well as the translations. So you could have used that instead. I'm just showing you a different method of achieving the same thing.